Did you ever have this experience as a kid? You're driving along in a vehicle and you're looking out the window and everything is passing by as it normally does, but then a semi-truck comes up and begins to pass you. And you think, oh my gosh, are we going backwards? That's a pretty interesting phenomenon, and it caught the eye of scientists as well. One scientist in particular spent a lot of time looking at this. He's a pretty smart guy. You may have heard of him. His name is Albert Einstein. Yes, Albert Einstein spent a bunch of time talking about how objects are moving relative to each other and how they appear to move. This concept of relative motion is the root of one of his biggest theories, the theory of relativity. And so we're going to get into the basics of what this means and how things look from different perspectives, and we're going to take a look at that right now. Okay, so when talking about motion, motion has to be described relative to something else. So it basically means compared to something else. If you say you're driving down the highway at 100 kilometers per hour, it has to be compared to something else. And usually we always compare to what we consider to be stationary, which is like the ground. So I'm going 100 kilometers per hour relative to the ground. But we can also consider how things look from different people's perspective. If I'm moving in the vehicle, everyone seems to be going past me. But if I'm on the ground, it looks like the person in the car is going the other direction by me. So looking at different people's perspectives is also called looking at their frames of reference. And we're going to do a little introduction to how that works with looking at a moving sidewalk at an airport. These are kind of like flat escalators that move along the ground to help people get to their destination faster. So let's consider this simple scenario where the yellow person is on the ground and we're going to consider their reference frame and see how things move compared to them or compared to the ground. So someone comes by on the moving sidewalk, this blue person, and we see them moving, in this case, to the right or at positive 2 kilometers per hour. This is positive 2 kilometers per hour in the yellow person's reference frame, or they might describe it as relative to the ground. But if we switch reference frames, and we now look at the perspective from the blue person, their ground is moving. So they're going to be staying stationary relative to their ground, but the other ground is going to appear to go in the opposite direction. So if we look at this, it looks like the yellow person is moving in the opposite direction. So from considering the perspective of the blue person, it looks that the yellow person is moving backwards at 2 kilometers per hour. This would be in blue's reference frame or relative to the sidewalk. Hopefully that makes sense for how we describe relative to, as we're going to take a look at a different example on some moving water. So in this case, we have a stationary person on the shore, someone floating in a tube, and another person cruising by in a boat. Okay, the person on the shore is moving, so we'll say that's kind of our stationary point relative to the shore or relative to the person on the shore. We have person moving in the tube, which is just staying up with the water. They're going at -2 because kind of backwards or to the left in our diagram. And then the person in the boat is going at -5 meters per second relative to the water. Okay, so we have kind of two motions going on here. And the question in this one is going to ask, how fast is the boat traveling relative to the shore? So anytime they say relative to the shore, relative to something stationary or the person there on the shore. Okay. So you might have an intuition about this, how fast it's going to look like they're going by to the guy on the shore. The water's moving at 2, and then he's moving at 5 on the water. So we're going to go 2 and then 5. It's going to appear like the person in the boat moves across that way at 7. Okay, that might have made some intuitive sense, but let's look at how we would draw a diagram to show this. So there's going to be some rules for how we're going to add velocities, or what I call simultaneous velocities. Okay, so we're adding vector rules, which we did for displacement earlier on in a previous video. Very similar to that. We're going to use arrows, and they're going to show the direction that it's pointing, and the length of the arrow is going to be how fast it's going. Okay, so we're going to have to add the vectors head to tail. That's important. One vector after another, basically one after another is head to tail. Any order doesn't matter the order. The result, or the overall velocity at the end, is the tail of the first to the head of the last. Let's take a look at how that looks for this scenario. I draw the water going at 2 kilometers per hour, then the person moving at 5 kilometers per hour relative to the water. I add them head to tail, tail of the first, head of the last. I get 7 kilometers per hour as my total. I realize I switched from meters per second to kilometers per hour. There we go. Now it's in meters per second, consistent with our other diagram. We're going to keep that motion similar, but now I'm going to flip the direction that the boat's going to go. So now we're going to have the water moving at the same speed. And now the boat's going to come this way at 5 meters per second. And once again, we're going to consider how fast does it appear that the person in the boat is traveling relative to someone on the shore. So again, from the picture, you might think, okay, we're going this way with the water at 2 meters per second. The boat's coming back this way, and he's got to battle against the water. So he's going to be traveling slower relative to the shore because he's got to fight against the water. And that's exactly right. We have a -2 and a +5. He's going to be going at +3 relative to someone on the shore. And we'll show that with our diagram here again as well. Start with the water, add the arrows head to tail, one after another, 5 meters per second. Now from the tail of my first one to the head of the last one becomes 3 meters per second as their velocity relative to the shore. For the next examples, we're going to look at things from a different perspective. We're going to look at from above. So now we're looking down. We can see we have the person in the boat right here, and here's the person stationary on the shore. We don't need the person in the tube anymore because we're going to show the movement of the water with this grid. That's going to show the moving water. Okay, so if the person was just sitting in the boat not paddling, the water would move and push them back in this direction. But remember, they're not stopped. They're going to be moving at 5 meters per second this way. But now we're going to make it a little bit trickier with a question saying, how long does it take to drive 50 meters in this direction? So let's put up 50 meters on the shore there. 50 meters in this direction, how long is that going to take them? And a reminder that the water is going 2 meters per second backwards. Okay, so I'm going to be driving forward. This will be just keeping up with the water. They're going fast in the water, so they're starting to come this direction. And now they've covered 50 meters at this point. How long would it take them to do that? Travel 50 meters on the shore. We would start the exact same way with adding those vectors. I'm going to shift the 5 down, shift the 2 up. I'm going to add them head to tail. This time I did it in a different order. I did the 5, then the 2, but reminder, the order doesn't matter. So this should still work and should give us the overall velocity of 3 meters per second. Okay, so now that we know that we're going at 3 meters per second relative to the shore, it's like we're going 3 meters per second on the shore. So to find the distance I travel on the shore 50 meters, or using that distance, and I know I'm going at 3 meters per second, we'll just be able to use v is equal to d over t, uniform motion from that previous lesson. So figure out how fast we're moving relative to the shore, and then use the distance on the shore. So we'll throw up our blackboard here. We're going to go v is equal to d over t. Rearrange for time, I have d over v. 50 divided by 3, and it should take 16.7 seconds to travel 50 meters. My animation was sped up a little bit, but you get the idea with it being 16.7 seconds to travel an actual 50 meters. Okay, now we're going to make it a bit harder because we're going to go vertically up the page now. We're going to try and cross the river, and we're once again going to try and go that 50 meters, but now it's in the y direction. It's not going to be just that easy though, because remember, we're going 2 meters per second to the side. So if they weren't paddling upwards, they're just floating down to the side. But now we're going to try and cross. So now I have simultaneous velocities, one in the vertical or the y, and one in the horizontal or one in the x. So what's this going to look like? It's going to look like this. The boat's going to travel up at an angle. I put a kind of darker version there of showing its original position, and it's going to be traveling up at an angle. This scenario is the main point of the video, as this is really common questions that you get in grade 11 physics. And there's kind of 2 types. There's some that ask, where do you end up? And there's some that ask, where should you aim? We're going to start with the where do you end up questions, and this would be kind of an example of one. So given our scenario, it says a boat drives 5 meters per second north relative to the water on a flowing river that's 50 meters across. The river is flowing at 2 meters per second west, and then there's 3 types of questions that can ask you. What's the velocity of the boat relative to the shore? That's why we talked about relativity at the start. How long does it take to cross the river, and how far west or downstream will the boat end up, or will it be when it reaches the shore? Let's start with the first one, looking at the velocity relative to the shore. So remember, this is how the boat is going to move, and relative to the shore means relative to something stationary. So compared to someone not moving, they're traveling up at that angle. We're We're going to use the same diagram that we used before by adding head to tail. So I start with the water. Now I start with the 5 meters per second going upwards, once again added head to tail. Now my result from the tail of the first to the end of the last shows that angled direction relative to someone that is not moving. So to find that, fortunately this is a right angled triangle when I have my x and my y. So we can just use Pythagorean's theorem here. So we'll bring up our blackboard up there. We're going to have 2 squared plus 5 squared square root, and we get 5.3 meters per second for that diagonal line. But unfortunately, that's not quite all we have to do because it asks for the velocity relative to the shore. We need the value, but also the direction. So we look at this triangle we have here and here. That's our opposite and our adjacent. So we're going to use tan to find that angle. 5 over 2, we get 68 degrees north of west. So this angle right here is from west, and we are north from there. So north of west is how we describe that. If you need a recap, that was done earlier in chapter 1. Next, looking at how long to cross or how long to cover that 50 meters. Similar to the previous one, we're going at a constant velocity, but we're moving up at this angle, and we can see on the triangle there's 3 different velocities. So we have v is equal to d over t, but which velocity do we use? And it's really common for students to select the 5.3 meters. But that's actually incorrect, because if I look at the 50 meters is in the vertical direction, and the diagonal 5.3 meters per second is horizontal. We actually travel more than 50 meters in the horizontal. That line is longer in the horizontal than just the vertical 50 meters. So if I'm looking at just changing in the vertical direction, 50 meters, I need to know how fast I'm going up in the vertical direction. That's the velocity that we're going to use. So how fast are we crossing the shore up is actually just the 5 meters per second, that pink line. So you always have to match your velocity and your displacement, that distance we're traveling, in the same direction. So let's throw up our blackboard once again. V is equal to d over t. We're trying to solve for time, and we're going to have to use the 5 meters per second. And we get an answer of 10 seconds. 10 seconds for our time to cross 50 divided by 5. Okay, so make sure you match the direction and the velocity in the same way. And the last one we're going to look at is how far do you end up downstream? Okay, so we were aiming this direction. We didn't hit up here. We went downstream in that direction significantly to the west. So how far did we end up there? We'll look at the diagram, and once again, it shows we're moving to the side. And just like I said in the last one, we're going to have to look at the velocity in the direction we're asked about. And we're asked about how far west down the shore. So we are going 2 meters per second west or down the shore. How long did we travel? Well, fortunately, in the last one, we solved that we were taking 10 seconds to cross. So for the whole time we're crossing, 10 seconds, we're going down at 2 meters per second. So use v is equal to d over t once again. But now for our velocity, we're going to use the 2 meters per second times 10 seconds, and we get 20 meters. By the time we reach the shore, we're going to be 20 meters downstream. So I hope those where do you end up questions are making sense. And now we're going to attempt the where do you aim questions. And these are a similar scenario, but they have a target. So say we're trying to reach that dock. The boat wants to get towards the dock, and it doesn't want to miss. Reminder, if it's just aiming for the dock, the water's going to push it to the side. He's going to miss far west. In the last one, we had 20 meters that he missed to the west. So now we got to make it so where do I aim my boat so that I get to that dock? So let's see how a question would read, where to aim. It says a boat is trying to reach a dock that is 50 meters north. The boat can drive at 5 meters per second relative to the water, and the water is flowing at 2 meters per second west. Very similar setup. But where does the boat have to aim so that it reaches the dock, and how long will it take to reach the dock? Let's start with where to aim. Okay, so we said that if he aims directly up, he's going to miss. He's going to go to the west. So how we have to change the boat is we have to tip it in this direction so that we're going this way to kind of cancel out the movement of the water that direction. So what's this going to look like? When the boat drives, it's going to look like this. He's pointed this way, but his movement is going straight up towards the dock. How does this really make sense? Let's go back to that vector diagram. So the water is pushing us 2 meters per second west, so we can see that's where we would end up. But now I have to drive back this direction. So I drive my angled vector there, going towards the dock, and the result is going directly upwards. Another way to kind of think of this is I have to tilt that pink line so that its x component is going to cancel out the water. If it's just straight up, the water is going to push us to the side. But if I tilt it this direction, the x part, which I would show right here, this component of the 5 meters per second, if I show how much are we driving this direction, is going to be that 2 meters per second in messy writing to cancel out that 2 here. So we're driving against the water at 2 meters per second. It's pushing us this way. That cancels out all side-to-side motion, and all we're left with is just going directly upwards. Okay, so how much do I have to tilt over this pink arrow so that it cancels out the 2? Well, we're going to use this, again, right-angled triangle, and we're going to do some trig. But different from last time, now I have the hypotenuse as 5 and the adjacent as 2. So we're going to have to use cosine and inverse of that to get the angle, 2 over 5. And get that we should aim at 66 degrees north of east. So that's right here. We have to aim north of east. Okay? As much as I like that for showing it on the diagram and how the boat moves, if I was drawing this on a sheet of paper on a test, I would actually draw it the other way because order doesn't matter. So on a blank page, I would first put the boat and then I would put its destination, just like a circle up there to show where it's supposed to go. The next thing I would actually put is the water. The reason why I'd put the water is I don't want it to push me away from the destination. I want it to push me to the destination. So I'd put the water showing going towards the dock. That's what I would do next. Now your last arrow is I have to go into the water. It's going to push me back and I end up going towards the dock. It's the same diagram, just different order. I did pink attached to blue and then from the tail of pink to the head of blue as my result. Why do I like this one better? Because I think this shows a little bit better that the boat has to be aimed in this direction. It was a bit hard to know which angle to do on the last diagram. This kind of shows clearly the boat is aiming in this direction. You can see it rotating to aim in that direction. So let's make sure we get the same answer. So I'd use, in this case, I have my hypotenuse and my opposite. So I'm using sine in this case, and it might be starting to look like we're going to get a different answer. And we do get a different angle. It's 24 degrees this time, but it's 24 degrees east of north. So what that means is from north here, it's 24 degrees east. This is actually the same answer as what we had before. Because if we had the previous one of 66 degrees north of east, it's describing the same angle. Let's look at this angle right here. I described this one right here, and I'll put that in red here, the 24 degrees east of north. And in the previous section, I described this way. I just used east as the reference, and that was the 66 degrees right here. So they both describe the same arrow. It's just if you're referencing north or referencing east. So both of those work. Whichever one you're more comfortable with, you can totally do that one. And let's finish up by looking at the last question. How long does it take to get to the dock? Well, let's look at that motion again using this triangle. They're traveling just directly upwards. Okay, so similar to like we had in the last case, if I'm traveling 50 meters upwards, I need how fast I'm going upwards. And 2 meters per second, 5 meters per second are not the velocities going directly upwards. So we need to use Pythagorean theorem once again to solve for how fast we're going upwards. So throw up our blackboard here. We're going to have 2 squared plus b squared is 5 squared because 5 squared is my hypotenuse in this case. And I get 4.8 meters per second, 4.58 meters per second as how fast we're going vertically. That would be right here on the triangle. So now that we know how fast we're going up and the distance that we travel up is that 50 meters, once again use v is equal to d over t, or t is equal to d over v, my distance, that 50 meters, and I'm going at 4.58 meters per second north. So we divide those and we get a final answer of 11 seconds to cross the river. It's a little bit longer than last time when we aimed straight up because some of our effort is going into canceling out the water there, aiming against it. So we're going to be traveling a little bit slower to cross the river. And that is it for our video today. I hope that helped you to understand a little bit about relativity and also how to solve these boat questions on a river with where you end up and where you aim. Thank you so much for watching this video, and I will see you in the next one.